go. So this afternoon, gentlemen, let me introduce us on how to use rational method, and then I will show us how to use a computer application, which is a software called SWIM, Stormwater Management Model. That's what we're going to be using to model it. So now this is the layout we're going to model. What you have here is about catchment. This is catchment A, this is catchment B, this is catchment C, this is catchment E, and so on and so forth. So this catchment represents districts, estates, cities, areas, and so on and so forth. So it could be more expanded. This is a bit irregular, but in real life, it's not going to be regular. It's going to be, very, very natural looking, different shapes. But for the purpose of this training, for the purpose of learning, we just have to make it to look regular. So these are the Siwa lines being on top, the drain lines being bottom. So this line effectively represents two systems. It can represent the Siwa system. It can also represent the storm system. Okay, remember what I told us yesterday. The difference between the Siwa system and the storm system, one of the differences is that the Siwa system is usually very small, done with PVC pipe, and it's usually located from 1.2 meters to 1.5 meters below ground level. The storm Siwa now comes on top. The storm Siwa is usually made up of concrete pipes, concrete drains, sorry. Okay, concrete pipe also. It could be rectangular, it could be trapezoidal, it could be rectangular, trapezoidal, it could be circular. And it can be made up of concrete. And it's usually very huge. It can range between 0.9 to about 3.03 meters. But Siwa lines are usually between 150 mm pipe, 150 mm, and let's say 600. I don't see a Siwa line being more than 600, because by the time you get to 600, it must have reached the treatment plant. And besides, the discharge of a Siwa line is usually very small. It's usually very small because it basically takes care of the water intake of the residents. It usually takes care of only the dry water flow. But the stormwater line, stormwater system, takes care of the precipitation. It takes care of the hydrology of the area. So in this study, we are assuming that at point 4, that is where you have your outfall. This is where you have your outfall. Okay, and so here are houses that will drain, and then when it gets here, the catchment B or Wuse or Lekki will join it. When it gets here, Aja or Buzape will join it. So what you see here are really big units. And then at the end of the day, they will go to either here now becomes the treatment plant if you are designing for Siwa, or becomes a water body, an outfall if you are designing for stormwater. Then you prepare an Excel sheet showing this, showing the beginning of each point and the end of each point, the length of each section. Then this over this divided by this will now give you the slope. The height difference divided by the horizontal distance will give you the slope. So the next thing we did yesterday was we now characterize for the stormwater, what is the characteristics of the catchment? What percentage is contributing to runoff? And to do that, you need to compute their peak runoff coefficients. So each of the elements that constitute the catchment, we listed them. All the streets make up 12% of the catchment. All the roofs make up 20% of the catchment. Then the others make up 5%. Gardens make up 63%. So at the end of the day, you now take a mean weight average of this. And when we took a mean weight average, we got about 37%, which is 0.37. You take the average of this. If you take on a normal average, you will not get 0.37%, but you have to take what they call mean weighted average. And this is what we mean by mean weighted average. Here, mean weighted average means you multiply the coefficient of each area times the area, then divide by the total area. This is a more accurate and a more scientific way of taking average. It will capture precisely the exact average relative to the standard deviation and relative to the values of each individual of the group. I will not elaborate much on that, but that is what we call weighted mean or mean weighted average. It is different from normal average, which is plus all of them together and divide them by their number. So now for other parameters to design the storm, we use a storm of 10 minutes because we are looking at a rural area. And based on that rural area, we are now looking at the population density of 100 people per hectare, 100 capita per hectare. We also assume for the Siwa, for the foul Siwa, that the water consumption per person is about 130 liters per capita per day. And based on code and standards, and safety factor, we use a safety factor, otherwise called peak factor, when it comes to water design of 2, water reticulation design. And then we also added a parasite water factor of 0.1. This is just like another additional safety factor. Then for the pipe roughness, we assume we are using concrete pipe, and the pipe roughness is about 1.5 for the stormwater. Good. So to calculate for the Siwa line, we multiply the water demand by the population equivalent, by the safety factor, and then we added the parasite water, and it gave us about 0.401 liters per seconds per hectare. In ideal case, we are supposed to have the value in liter per seconds so that we can easily go to our charts and dimension the pipe and size the pipe. But because we are working based on land use, so we now got the value in liter per seconds per hectare. The next thing we need to do is now, for each area, we will now multiply by the hectare. If we multiply by the hectare, we will now get the exact discharge going into that pipe. So you can assume this to be like a specific discharge relative to hectare per hectare. For the stormwater, how do you calculate runoff? To calculate your runoff, represented by Q, you multiply the rain intensity, which is a function of duration and frequency. In other words, your rain intensity must capture what duration it is and what the frequency is. And then you multiply it by the impervious area. Now, I did not multiply by the area, but I multiplied by the impervious area, meaning that this impervious area is the area contributing to runoff. If you expand it, the impervious area is gotten by multiplying the total area or the subcatchment area by the specific runoff of that catchment. Okay, based on the distribution of roof, road, green area, football, and every other distribution of the area. Then we now also got the mean weighted average for the whole layout to be 0.371 based on this. So how we got 0.371, you simply multiply this by the area, by the percentage, multiply this by the percentage, multiply it by the percentage, and at the end of the day, you divide by the total percentage, which is 100. That will give you that 0.37. The next thing we do in order to calculate our runoff is that we need to determine D and N. What duration are we going to take and what frequency are we going to take? And the standard we are using, which is a German standard, says that if you are designing for a rural area, you should assume a storm. If you are designing for a rural area and you are designing for drain, which is normal storm, you should use a return period of 1 year. If you are designing for a surcharge means like what somebody asked yesterday. That was Muyiwa or so. No, Aliyu. I can't remember who asked that question. Surcharge means you are not just designing for the water to be accommodated in the drain, but you're also assuming that the water has the possibility of overflowing. That is what we call surcharge in water reticulation, in water design. You don't call it overflow. Okay, overflow is a good word, but the appropriate word is the water is surcharging. So here, if you are designing for surcharge, in other words, you're making allowance for surcharging, you use 2 years return period. If you are designing for flood, you use a 10-year return period for a rural area. For residential area, you use 2 years for storm, 3 years for surcharge, and 20 years for flood. If you are designing for flood, it's a different thing than when you are designing for normal conveyance system. Conveyance system is rain will, there will be precipitation, there will be storm event or rain event, and the water, the drain will successfully discharge it, carry it and discharge it to the open stream. If you are designing for city centers, which is a higher risk area, you use a storm for 2 to 5 years, a surcharge of 5 years, and for flooding, you use 30 years. If you are designing for underground system, which is a higher risk area, also much higher risk area, you use a design storm for 10 years. When we are talking about all these things, what do we mean by this? Somebody will ask. Well, this is what we mean. This is what we mean. In the highway design manual, we got to know that the IDF of all the cities in Nigeria have been captured. So if you want to read, so good. So this is it. So if you want to read, for instance, I'm designing for, which city am I designing for? Okay, let's say I'm designing for Jos. No? Kaduna. Let's say my design is for Kaduna. This is the IDF. This is where I'm going to take my rainfall data. This is, you don't need to go to water board or river basin to ask for rainfall design data. This is where you're going to. How many of us have this drawing, have this chart? Please open it. There are 2 of them I gave us. Nigerian Code of Practice. There are 2 of them. Please, can we quickly open it? Let me share it. Give me 1 minute. Let me share it.
I can't hear you. I can't hear anything.
Okay. Okay. I'm sorry. I think it's from my end. I don't know why when I click something. So now, as we are saying, we started with. Thank you. We started with the um, rational method. This is our layout. This is our chart. From this layout, you come up with this. Then from here, you come up with this also, where you now show the catchments, how they are all distributed. Then this is your population density. This is the storm. We are using a 10-minute storm. And then the water consumption is about 130 liters per capita per day. The peak factor for the Siwa system, we're using 2. Yesterday I told us that this peak factor is that factor that takes care of your losses, your population growth, your future development, population forecast, and all other unforeseen factors that might influence your design. Then here we calculated the dry weather flow, the wastewater flow going to the Siwa line, Siwa, and that is your water demand plus times your population equivalent times the safety factor, then times the infiltration, parasite infiltration water. And so we assume 130 for water demand, multiplied by 100 hectares, 100 capita per hectare, 100 persons per hectare. We divided it by this to convert day to seconds. We multiply by 2, which is our peak factor. And then we added the infiltration water. Everything will now give us 0.401 liters per seconds per hectare. So this is like a specific flow per hectare. Then the next thing is for the storm flow, we multiply the rainfall intensity by the impervious area. And how did we get the impervious area? It is by multiplying the peak factor, peak runoff, by the total by the subcatchment area. And how did we get the runoff, peak runoff? By calculating the individual runoff of each area. Gardens are grass, vegetation cover. They have a low peak runoff. They don't contribute much to runoff. Only about 10% of it, water that falls on it flows over land and contributes to runoff. But for the streets, about 90% of them flows into the drain or contributes to runoff. Roof, about 95% of it flows into the runoff, and so on and so forth. So this is, we also say that the slope also influences the runoff. After that, we now went to how do you calculate your sewer and stormwater. And we said here, you choose your N, you choose your D. Your D is your duration. What's the rainfall duration? Ideally, just choose between 10 and 15 minutes. Then for the frequency, depending on what you are designing for, you choose your frequency from here. If you are designing for stormwater, ordinary discharge, you use, and it's a city center, you use 5 years. So for our design, we're using 5 years. We're designing for city center. We're not designing for flood. We're designing for storm events. Okay, with or without surcharge. The next thing you choose is you consult your IDF curve. So in consulting your IDF curve, you go and choose the city. You go and choose the city you are designing for. This is for Kaduna. This is for Castina. Castina, you can see, and choose the IDF for Castina. Then if I come here now, I'll choose the 15 minutes rain. I'll read it off against the return period. Either is for this our design, we're using 5 years. So here is about 140. So the rainfall intensity in Castina is 140 millimeter per hour. Then for other cities, for Lagos Island, let's look at what Lagos is. For a 15 minutes rain in Lagos, and for a design period of 5 years, Lagos is giving us 160. You see the difference? Let's go for a city that's far north and see what the value is. Maiduguri, good. Maiduguri, for a 15 minutes rain in Maiduguri and for 5 years return period, that is about about 130. Excuse me, and so on and so forth. 1 minute, gentlemen. Let me. One of us is trying to join us. Let me just send the message to him, and then we'll continue, please. So please, while you're waiting, can you go through can you open the IDF curves? Can you open the sheets on your computer and go through it? Locate your city, and then know how to read it. Can you just open your city, either in volume 1 or in volume 2? Can you locate your city? If you can't find your city, let me know, and I'll tell you what you do when you're doing a design for that city. So do your city, and then get me the IDF curve for a 5-year return period. What is it giving you in your city? Let me put it as an example, as an exercise. As a question. What? Okay, 1 minute. What rainfall value will you use for your city? If you are designing for a storm event of 10 years return period, 10 years return period, that means the frequency is 0.1. I put it this way, n equals 0.1. And the duration is 15 minutes. So can you all look it up in the chat? So go to the chat and find the city. So my city is FCT. I don't think there's FCT here, but I can use Lokoja comfortably and justify it. So for my Lokoja, this is my 15 minutes, and I'm designed for a 10-year return period. 10-year return period means that's almost like I'm designed for flood. So let me use 5 years, because anything from 10 years should be flood design. I'm designed just for drainage, simple drainage. So for 15 years against 5 years, Abuja is about 120. I was saying 100 yesterday, so it's actually 100. Okay, 100 is for 2 years. That means for small drains. So can you look it up and then chat me up? Tell me what you got, please. Okay. Please, when I ask something, always reply. It gives a good feedback. Somebody say can't hear me. Okay, what was that? Okay, think that's already gone. So what did you get, please? The duration for 15 minutes. 10 or 15 minutes. It cannot be more than that. Between these two, that's what the value you choose. Then you read it against whether it's 2 years, it's 5 years, and so on and so forth. Okay, if I'm not getting any feedback, that means I'm free to continue. So let me quickly continue. So back to what we are saying. So after you consult your IDF curve, the next thing you do is that you calculate your wet weather flow, the wastewater flow, or the runoff, two of them. Then after that, you use your chart, you choose the adequate pipe, considering the security factor. And required pipe depends on the discharge, the slope, and the roughness. Good. So after the discharge, you now calculate the real velocity, which you can read off from the chart also. You calculate the flow time, which I'm going to show you how to do. And then you now go and do the design proper. So now, let's take one example. This is the example we are going to take. Here. Now, in your chart, there is go to under urban design lecture material. You will see chart of rational method. Please open it with PDF. Chart of rational method. Okay, Ikeja 180. I mean, okay, Ikeja 180 for, is it for 5 years or for 10 years? Okay. So this is the chart you're going to fill if you want to do rational method. So I'm going to show us how to fill this chart. Please pay attention. This place is very, very critical. And it's very important that we understand how to use it. This is very, very critical and it's very, very important. So the first thing you do is, given that chart, you list the pipe, the number of pipes, pipe A to pipe H. Okay? A to H. Remember, this is the pipe. A, B, C, D, E, F, G, and H. So, after listing the pipe, you list the start coordinates and the end coordinates. The start coordinate and the end coordinates. It helps you to know the beginning of the pipe and the end of the pipe, so that you can calculate the slope and the velocity. You can calculate the slope, and the slope in turn will help you to underestimate the pipe size. So please, let me give us 2 minutes for us to open this chart. Open this chart and then try to compare it with this. Are you with me? So, okay, this is it. So the next thing you do is you list the area of each catchment. Catchment A has an area of 15.3. Here, you list the area of each catchment. So this is ACS. ACS. So catchment A has an area of 15.63. Catchment B has 5.47, and so on and so forth. You list every one of them. The next thing you do is you multiply the area by the wastewater flow. The area of each by the wastewater flow. Here, this is the wastewater flow. So, for instance, for catchment A, the area is 15.63, and then the wastewater flow is about, as given here, which is 0.401 liters. How did you got to that? Let me use my whiteboard. Catchment A. All right. Catchment A. The area is 15.63. Okay. And the wastewater flow, they are about the population, the wastewater flow is Q equals BQ is equal to AV. Open up these charts with you here and be looking at it. So I'm going to replicate this. I want to replicate this. So that will give you wait a minute. Let me So, sorry, pardon me. I think I had some hitches. So QV. So now the water demand is 130 per person. Multiply. What is the population equivalent? 100. What is our safety factor? Our safety factor is 2. Then we now add the ingress water. Okay. So at the end of the day, we got 0.401 liters per seconds per hectare, because this is still per hectare. But then what we now do for catchment A, so the discharge, the sewage discharge will now be 0.401 multiplied by the area. This is what you get, 6.29 liters per seconds. So that's why you have this 0.401. The reason is that you are talking in terms of hectares. Okay. So now you have the area. You now multiply by the area. You want to ask question?
UV again.
Sorry? I can't hear you, sir. It's breaking. Put it in the chat. Put it in the chat. That's why I said, just ask the question in the chat. Sometimes network can really be difficult. If you put in the chat, I'll get it. Engineer, can you chat me up? Can you mute and just chat up? We can't hear you well. Can you just chat? Put it in the chat. Put your question in the chat box. So now this becomes the discharge coming for the Siwa line. So with this one now, if you want to size the Siwa, all you need to do is now to go to your chart. And Siwa is PVC pipe. So I'll now go to my chart using my chart of 0.1 for PVC. The slope is given in that table. Quickly. The slope for catchment A, look at catchment A. The slope for catchment A is 1/200. 1/200. Using calculator, what does it show? What does it mean? 1/200 means 1 divided 200. So the slope is 0.005. From what we said yesterday, I said that somebody will give you this as a slope, or the person will give it to you in percentage. If I'm to give you the same slope in percentage, I'll simply multiply it by 100. So it's either I say 0.005 as a slope without any units, or I will give you 0.5%. It means the same thing. But for our chart, I will multiply this 0.005 by 1,000 or percentage by 10. 5. So that means 5 is my slope on this chart. It means 5 is my slope on this chart. So 6.27 is somewhere here against 5 per thousand. This is 5 per thousand. It's giving me something between 100 and 125 mm. So the optimum pipe size for this discharge is 125 mm. Oh, thank you so much. That's why I don't like going to the whiteboard. So from the whiteboard, okay, that means I'll be using Word. Let me use MS Word. It will help us better. So for the catchment A, whatever. For catchment A, we got let me copy it from the whiteboard. So from catchment A, this is what we have in catchment A. Therefore, from the chart, okay, we now say we read 6.27 against 5 per thousand. Remember, from our slope, from the table, from table, the slope is 1/200, which is equal to 0.005, which is also equal to 0.5%, then which is now equal to 5 per mil. This is well understood. So now I will read 2.627. I'll go to my chart. Meanwhile, I asked us to print this chart yesterday. I don't know how many people have printed it, but please try and print this chart and keep it as a very, very important file for you to do your pipe sizing. So here now, I will now say 6.27, which is somewhere here, against 5. Is falling in between two. Is falling in between two pipes, 100 mm pipe and 125 mm pipe. Yesterday we said when you have something like that, you are expected to choose the bigger of them. So here I have 100 mm, here I have 125. So I'm going to choose 125. So that means the optimum pipe size for pipe A is 125 mm. But in bracket, I will say use 150 mm. Why? Code recommendation. The code recommended that you must use a minimum of 150 mm pipe, which is 6 inches pipe, for your Siwa network. If you see anybody using 4 inches pipe, 4 mm, 400 mm pipe, it is wrong. You can use that for your house, inside your compound, inside your house. But once it's on the street, the standard says the minimum standard is 125. So even if I got 125, I'll put it down, but I know that I'm using 150. What do you call it? 150 mm. So the next thing now, let's do for catchment B. We're going for catchment B. Catchment B has an area, has a slope of 1/300, an area of 5.47. Okay, so for catchment B, do I have to go do calculation again? No. So let me call this catchment. Sorry, this is catchment B. So I copy it. I come here. So for catchment B, all I need to change, this calculation remains the same. This calculation from this point remains the same. All I need to do for catchment B now is just to say, I'll copy this. It's the same thing. The second one will now be the Siwa size will now be 0.401 multiplied by 5.47. You know, this I really enjoy this because this is telling you that if you are given a plot of land, a virgin area, all you need to know is to do the design based on the size of the land. But then what will guide you also is the land use. Okay, you use the size of the land and just multiply by the flow coming per unit hectare. But now the land use will guide you in this 100 here. It could be 300, it could be 400, depending on whether it's low density, high density, or medium density. Are you with me? Are we together? Okay.
Yes, we are with you.
Thank you, sir. That's a good one. So now, this will now give you, what will it give you? If I want to see what it will give me, I'll just go to this chart. It will give me 2.19. Somebody can use his calculator and see if I'm wrong. 2.19. This time around, it's not going to be 2.19 liter per second. It's not going to be liter per second because I've multiplied it by the area. So area will eliminate the hectare. So this becomes my point. So with this, I can now go and size the size of the pipe will now be based on this. But let's calculate the sizes first. Why I'm not going to size this now is because if you look at this exercise, catchment B is receiving discharge from catchment A. Catchment B is receiving discharge from catchment A. So catchment B is 2.19, but the discharge flowing in catchment B is going to be the addition of catchment A plus catchment B. Because the catchment B is downstream of catchment A. So when I was teaching some people water reticulation last time, I told them that the specific demand in catchment B is 2.19, but the wastewater flow at any given time is going to be the wastewater flow coming from A plus the base demand for B. So you can look at B as the base, as a base. The base, the houses that are connected to B are giving you 2.1 liters a second in all the houses. And if you look at it, you see that B is a little bit small compared to A. While A is giving you 6.29, B is giving you 2.1. But the flow in B is the aggregate of two of them because A is emptying into B. A is emptying into B. Okay, so therefore, B is going to size B, size of pipe B is going to be 2.19 plus 6.29, okay, which in brackets is B plus, plus A. And that will give you it will give you 8.46. That's how we got this 8.46. So this is my A, this is my B. This is, so after getting my A, I sum, this is summation. I now accumulate it. So B becomes 8.46. 8.46 liters per seconds. Then I now go to my chart. When I got to my chart now, I'll look at 8. I'll go to 8. This is 8. 8.46. I'll read it against, what's the slope? We've not calculated the slope of B. Slope of B is 1/3. Slope 1/300 from the chart. 1/300 means 1 divide 300 equals 0.003. I guess you know what that means. So the slope is 0.003. So that means from our charts, in percentage, that means this is 0.3%. From our chart, that will give you 3 per mil. Okay, so I'm going to read it against 3%. So 8.46 against, so 8.46 versus 3. Versus 3, yeah. And the value is, going to be, this is 8 against 3. The value is exactly, no, the value is in between, 125 and 150. 125 and 150. So I'm going to use 150. So the value is going to be 150 millimeter pipe. Is that understood? Any question? Any questions so far? Any question? Somebody say, I don't have the chart. Okay, Grace. Okay, I'll send you the chart now shortly. I'll send you the chart. Okay. So let's continue. If there's no question, we will now continue for the other pipe. So we've done pipe A and pipe B. We've done pipe A and pipe B. So let's do pipe C. Pipe C, the slope is still the same thing as pipe B, and the catchment area is at 14.06. Somebody just joined us. Please, you have to mute yourself.
This is Ilo.
Yeah, Ilo, mute. You want to ask question? Okay, so let's continue. So you can see the catchment of C is 14.06, almost as big as catchment A, and the slope is just the same thing. So that makes our work easy. So what we simply do is we now say for catchment, it's my catchment. For catchment C, everything applies except the percentage, isn't it? For catchment C, why should I be repeating this thing? It's the same thing. So for catchment C is simply 0.401 multiplied by the area, 14.06. And that will give us 5.64. You can confirm 5.64. So you go to your chart and fill it. You know, this chart is this is like your calculation sheet. Once you do it, you go to your chart and you fill it. Okay. And the lecture note too. Okay. So once again, you see all the values I'm getting, I'm filling it, you'll be filling it here. So we're in catchment C. The area is this. When you multiply by the flow per hectare, this wastewater flow coming in from that catchment, you get 5.64. Okay. Now, catchment C does not have upstream. So if we want to get the pipe size, we simply use this 5.6 against, we use 5.64 against 3. That's all. So I go to my chart. I'll go to 5.64. Sorry. This is 5.6. It will fall in between 125, 125. So it means catchment C, the value is 125 mm pipe. Am I right? Comma 125 mm. That's the pipe size for catchment C. If you can't get audio, you know, you have to log in again, and then say use computer audio. That's how it is done. Okay. So that is that. We've done for catchment. Oh, sorry. 125 mm. The next catchment now is catchment. Is pipe. Either you call it pipe or you call it catchment. It's the same thing. Is pipe D. Let's do for pipe D. Are you with me? Let's do for pipe D. Now, mind you, pipe D is going to be a bigger pipe. It's going to be big because it's taking tributary. It's a tributary. Is a taking flow coming from A, coming from C, and coming from B. Or simply put, it's taking flow coming from B and C, knowing fully well that the flow coming from A have already been included in the flow coming from B. So for catchment D now, these are the parameters. Catchment D has a size of 3.91 hectares. And the slope is 1/400. The slope of the pipe or the slope of the land, whatever you want to use, is 1/400, which is 0.25 anyway, 0.25% or 2.5 per thousand. And this is it. So take note of this. Okay. Somebody's asking me for the chart. You participated yesterday. The chart is in the cloud. Just go to the cloud and take it. Everything is in the cloud. Okay. So, pipe D, that's where we are now. For Siwa, we've not come to Stormwater. This is still a Siwa line, PVC pipe. Still a Siwa line. But the same process for Stormwater, only that the variable will change. We're going to use rainfall this time and not water demand. Wastewater. Not, we're going to use rainfall and not wastewater. Good. So let's go. You're doing well. So catchment D Catchment D now, represented by pipe B, represented by pipe D. Okay, what is the size? Good. So that would be 0.401 multiplied by the catchment, which is 3.91. That will give you 1.57. 1.57. 1.57 liters per second, of course. So we will now go to our charts. If you go to your charts, no, you can't go to your charts. Why? Because in actual sense, the flow, the catchment of pipe D, catchment D is, okay, let me put this way. Catchment D is contributing only 1.57, but the flow through it will now be its own flow, or let me put this way, will now be D plus C plus B. I will say note, B is already B plus A. Okay? What I'm trying to say at that point is that B has already, anything I'm taking from here now is already accumulation of this and this. So for pipe D now, flowing into this junction, what is flowing into this junction now will be whatever is coming from here, two of them will flow into this one. And that becomes 1.57 plus, what's the value of B? This is catchment B. Catchment B is 8.46. Is 8.46? 8.46, yeah, 8 point. Sorry there. And that will become 1.57 plus 8.46 plus 5.64. And that will give us, please, can somebody add it together? What did you get? You get 15.66. 15.66. So I'll go to my chart, to my calculation sheet. I'll go to my calculation sheet and I'll write it here. This is what you have here. Summation of this. What you have, what is written here is what is written here. Difference is this summation. Accumulation, this means accumulation. Why this is area times wastewater flow. ACS, A_CS multiplied by QWW, which is wastewater, specific wastewater discharge. So that gives you this 15.66. So this 15.66 now is now what we'll go and read against 2.5. So to size the pipe, sizing 15.66 versus 2.5. I don't need to start going again. I need to start going through again. This is the slope. So let me just copy it again. For the last time, I won't copy it again. The slope is 400, which is 0.25, which is 0.25. So this is how I got 2.5 per thousand. So if I go to my chart now, please, this time I want everyone to read it. Get me the value. I'm not going to read it. Can we read the value? Can we read the value? 15.66 against 2.5 per mil. 2.5 per thousand. What did you get? So I'll read it here. If you get your value, put it in the chat box. I'll pause this. Let me pause the recording. Resume recording. So next is pipe E. So pipe E, the same specific flow multiplied by the catchment area will give us 5.95, and the slope is 1/500, which is the same thing as 1 per thousand. Let me fast track it. So this is 1 per thousand. So the next thing we're going to do now is 5.95 versus 1 versus 1, and the value is 5.95, which is like 6 against 1. The value is 150 mm. It's in between here, 150 mm, and then of course the velocity is there. I'm not interested in the velocity because the velocity is met. The velocity is about 0.03, which is very critical because the optimum is 0.05. So if you go down like this, you get the velocity. If you go like this, you get the pipe size. Is that okay? If you go diagonal, left to right, upwards, you get the pipe size. If you go down this way, you get the velocity. So maybe I should be writing down the velocity also subsequently, though we can easily go back and do those ones. So the pipe size is now 150 mm, and the velocity is 0.4 meter per seconds. So this other one that we've done previously, we can go back and check their velocity. Like the last one we did, okay, like this one, let me quickly get the velocity at that point. The velocity at that point is 15 against 2.5. The velocity is 0.6. You can check on your own too. So it means this velocity here is satisfied. Is satisfied. While the velocity here is a bit critical. And what made it critical is because of this slope. Gentlemen, you know what this slope means? 1% means for every 1 kilometer, the head difference is 1 meter. For every 1 kilometer, the head difference is 1 meter. That's what it means. You know, kilometer is a 1,000 steps. It's a 1,000 meters. So it means if you walk for 1 kilometer, if you measure for 1 kilometer, the difference in height is only 1 meter height difference. So if you look at that, you see that that's a very, very gentle slope. So if you're laying pipe in that kind of, if you're laying your Siwa pipe in that kind of terrain, you should know that flow might be a problem. But the good news is that the flow is quite appreciable. It's at the minimum. It's at the edge. It's at the lower boundary condition. It's revolving around the lowest boundary. So it's still tolerable. So this is pipe E. So now let's go for pipe. What's the next pipe? The next pipe is now pipe F. So catchment F or pipe F. So when I say catchment F, is the same thing as pipe F. Okay. So I don't know if I have a smart guy in this class. I challenge you if you can do it for me. Let me just give you an idea of what to do, and let me see. Is the slope not 2 for E? Slope for E is, this is the slope for E. Slope for E is 1/5,000. Oh, 2%. Okay. Oh, somebody's making sense. Yes. Yeah, I'm wrong. But my being wrong, oh, that's a good observation. This slope is not 1%, gentlemen. This is 2. Thank you very much. Thank you very much. 2. So will that change my parameter? Let me check. So we are doing 5.9 against 2. Oh, this is cool. I'm really excited. Well, why should I be too surprised? All of us are engineers. So it's not like I'm teaching a primary school students. So 5.9 against 2%. Against 2%. 125. It is 125. Thank you so much. The value is 125 and not 150. But use 150 as recommended by code. Engineer, the person that made that comment, did you understand what I mean by code? Okay, engineer AGK is Ugu. Okay. Okay.
Yes, you said something about it, sir. I understand.
Okay, good. Sorry, a question is coming for you, but don't worry about it. Just answer it. Okay, now, so let's continue. So catchment F now, which is pipe F, is that's where we are now. So catchment F now, I wanted to leave it for us to solve it, but let me do it, and that will be the last one I'll do. The subsequent one, all of us are going to do it. So let's just look at the parameters of catchment F again. Catchment F is, the slope is 0.2% or 2 per 1,000. I don't know, there's a mistake here. Ignore this mistake, please. Let's just use 2%. They wrote something different here. Wrote something different here. It's a mistake. Remember, this lecture note is from University of Stuttgart. So please, I have to reference them. It's from University of Stuttgart. It's not me that prepared this. It's a professor, Professor Steinmetz. Now, if you look at catchment F, is a very small catchment. It is 4.69 hectares. So the slope is this. So in calculating catchment F, and then looking at how it appears, it is somewhere here. In as much as it's a small catchment, but it's going to carry a big discharge. It's going to carry discharge coming from another catchment. Therefore, in calculating catchment F, we now say catchment F is now 0.401. Nobody's asking me how I got this. That means everyone understood how it came about. Multiply by the catchment again. What is the size of that catchment again? 4.69. Multiply by 4.69. And that value of 4.69 is giving us, is giving me 1.88. So it's giving me 1.88 liters per second. Should I go ahead and just design with 1.88 and put the pipe there? No, I'll be wrong, because pipe F has, although has discharge of 1.88, it's a collector. Let me use the word. It's a collector for who and who again? It's a collector for B. No, I don't even have to put that. I will simply say is a collector for those closest to it. And I'll say it's a collector for D and F. D and E, sorry. Yeah. Knowing fully well that D already has B and C inside it. So I would say it's a collector for D and E. Therefore, flow at F is now 1.88 plus, what do you have for D? 15.66 and 5.95. 15.66 plus 5.95. And that will give you what? That will give you 23.49. 23.49 liters per seconds. So we now do 23.49 versus 2. So can somebody do it? What are you getting? Oh no, let me do it. Let me finish. Then all of us will do the next. So I'll go to my chart now. And 23.49 is almost 25 against 2. Yeah, against 2, somewhere here, and that is 250, between 200. It's falling between 200 and 250, and on the velocity angle, it's falling between 0.7 and 0.6. So that will give me 250 pipe, and the velocity is 0.7 meter per seconds. So assignment and break, like we did yesterday, is to serve both as assignment and as break. And I'm going to pause also. So can we help calculate for? Let's calculate for G and H. Let me give you an idea. G, anything you calculate for G, you just drop it there. You size it that way. You just size it. But when you calculate for H, you must add it, the value of F and the value of G. Are we together? So the assignment is what is the pipe size for G and H? In other words, catchments G and H. You have 10 minutes. So your time start. Let me pause. So sharing my screen again. This is the assignment I gave us. This is the answers. Good. Now for catchment, let's go again. Let's look at it again. This is catchment G. It has an area of 14 hectares, and slope is 1/3, 1/300, which is 0.3% or 3 per mil. Okay, and G is on its own. It doesn't have upstream. Nobody's discharging into it. So to do the calculation for G, is simply going to be something like this. The specific demand coming, you know how we got 0.401, multiplied by the catchment to give you this. You go to your chart and read it against this. You get 125 but the code says you should use 150 But for H, the catchment of H has a discharge of 0.494. And if you look at H is very small. Look at H, it's very small. But how come the pipe size is very huge? The reason being that although H is a small catchment, it is the tributaries of the other catchments are coming to entering into him. It's like a collector to other tributaries. Therefore, in the calculation, you now understand that H is this, but because there are other tributaries, its contribution to itself, G and F. So what you have here is H plus G plus F. And that value will give you 30 liters per second. So you see how this is how to design a Siwa network. So I will likely save this. I'm going to save this now and send it to us. So this is like Siwa calculation of pipe size for a Siwa network. And let's say some assumptions. Okay, let's put up assumptions. the number one assumption is that water demand is 130 liters per capita per day. Population, or you call it population equivalent, PE, is 100 capita per hectare. They didn't tell us 10,000 people, 1,000 people. But if you now know the land use and you know the area you're multiplying, once you multiply by the area, it will give you a number of persons. Peak factor is what? 2. Okay. I think these are the only thing we need for this one. Then we say parasite water. Parasite water on stroke linear factor. In bracket, I put it SF, safety factor of 0.1 to take care of leakages and infiltration water, liters per seconds per hectare. Everything is in hectare, remember, because you don't know the number of persons. So, but you can use the area calculation to augment every other thing. So that is that. So that is how to design your Siwa network. Okay. The next thing we're going to do. So what you have here, you now create a calculation sheet, and that is what you have here between this place and this point. You can see where you're written wastewater. The next thing we're going to do now is we're talking about stormwater. So this is, you now create a calculation sheet and put the area of catchment, put the flow, and put the accumulation flow, the summation. This is summation of the flow. So after this chart now you have here, you now use the value here to design your Siwa line, your Siwa network. And that's exactly what we have been able to do in this last 2 hours. So the next thing we're going to be doing now is to do for the stormwater.